Hi everyone, and welcome to the first of two videos going through some past paper questions on the topic of entropy and free energy. Now, the key thing about entropy to remember is that entropy is a measure of disorder. Okay, it's about how randomly organised the particles are. Okay, and this is the key bit that's going to be necessary for this question. So here it's saying entropy changes are an important factor in determining the feasibility of reactions, basically whether this reaction is going to be possible or not. Okay, and here we have four different processes, and it's saying for each process, explain why delta S, which is the symbol for the entropy change, but entropy is always given the symbol S, and this delta symbol always means a change. So delta S, why does it have the sign that's shown below? Okay. So we're saying for process A, the sign of delta S is negative. So if delta S is negative, it means the entropy is decreasing. So it means the amount of disorder is decreasing. So why is that? What's going on in process A? The key thing to look at here, we've got, first look at the state symbols, right? Everything is a gas here. And then you want to look at how many moles you've got. So we've got 2 moles of SO2 and 1 mole of O2, and it's turning into 2 moles of SO3. So we're going from 3 moles of gas to 2 moles of gas. So that's what we want to say here. So 3 moles of gas forms 2 moles of gas. So there is less disorder in the products. And there's a few things to be careful of when you're writing these kind of answers. One is, I think it's always a good idea just to show that you know what entropy is. Entropy is the amount of disorder. So if the entropy change is negative, it means there's going to be less disorder. But why is there going to be less disorder? Because we've got fewer moles of gas. Okay? But it's always a good idea, I think, to actually put numbers in. Okay, what about B? B is saying delta S is positive. So this means it should be getting more disordered. And this is because we're going from a liquid to a gas. Okay, so we can say a change of state from liquid to gas results in an increase in disorder. Process number C, here we've got hydrogen gas and oxygen gas making liquid water. So this is essentially the opposite. We've got gases turning into liquids. Okay, so we can say gaseous reactants form a liquid product resulting in a decrease in disorder. A liquid is less disordered than a solid. Okay. Sorry, a liquid is less disordered than a gas. Get it right. Gas is the most disordered, then a liquid, and then a solid is the least disordered, isn't it? A solid is pretty organised. Right, and then for question D, the sign of delta S is positive, so this should be getting more disordered. Okay, and so what we've got here is we've got carbon as a solid reacting with oxygen gas to make carbon monoxide gas. So we've got a gas on both sides, but again, it's not really as simple as saying it's a change of state, because we've got a solid and a gas and we're making a gas. But this goes back to this idea of how many moles of gas have we got. We started with 1 mole of gas and we've now got 2 moles of gas. So that's going to be more disordered. Okay, so there is 1 mole of gas in the reactants and 2 moles of gas in the products. So disorder increases. And that's a really important point here, that we don't just count the total number of moles, you just look at the number of moles of gas. There are 3 moles on this side and only 2 on that side, but there's more moles of gas here. Okay? A gas is so much more disordered than a solid that this is going to be much more disordered than having 1 mole of gas and 2 moles of solid. Okay. So those are kind of the wordy questions. And then you also get asked to do some calculations on this topic. So here we have some numbers. So, right, it's going about calcium oxide. Here's the entropy change, it's plus 178. We've got the standard entropies, and we've got various things to do here, right? So it's a 7-mark question altogether. Okay, so there's quite a bit to do here. Using the information in the table, show that the entropy change, delta S, for the decomposition of calcium carbonate is this. Okay, so this is basically calculate the entropy change, but we know what the answer should be. Okay, so we can check if we've got it right. So to work out delta S, the entropy change, we're just going to do the entropy of the products minus the entropy of the reactants. So we want the calcium oxide, which is 40, plus the carbon dioxide, which is 214, take away the calcium carbonate, which is 89. Okay, so we work that out. 40 plus 214, take away 89, is 165. But they're telling us that it should be 0.165, so something's dodgy here. This is because we need to be careful with the units. Okay, this is in units of joules per Kelvin per mole. Okay, always, always, always write units with every number that you've calculated. Okay, don't just write the number down. Make sure you put the units with it. Okay, so you can see what you've done. This is why there's a difference then. They want this in kilojoules, so we need to divide this by 1,000. And that is going to give us the right value. So it's 0.165 kilojoules per Kelvin per mole. Okay, so we've done that bullet point. I think this is useful to actually just go and tick these off, make sure you don't miss anything. Right, now it says show that calcium carbonate is stable at room temperature. So to do this is starting to look at free energy. Okay, because if it's stable, what that means is that this reaction is not happening. Yeah, because that reaction is breaking down the calcium carbonate. So if it's stable, we need to prove that this reaction isn't feasible at 25 degrees. And to do that, we need to use our equation for Gibbs energy. Okay. So the equation is delta G is delta H minus T delta S. You need to remember that equation. And then we can just substitute our numbers in. So the value for delta H they gave us up here was plus 178. Sorry, what am I writing? Plus 178 minus, then we need to put the temperature. Temperature is 25 degrees, but the temperature is going to have to be in Kelvin if we look at the units. So 25 degrees C, you add 273. So it's going to be 298 Kelvin. Okay. So that's going to go in there. And then delta S, we're going to use this value in kilojoules, not this value. Okay, because the value for delta H was in kilojoules. So we need to use the value here in kilojoules. Okay. So we need to work this out. And we get 128.83 kilojoules per mole. Okay, again, as we said before, always write units with your numbers. There is actually a mark for putting the units here. Okay, so make sure you don't miss that off. And I think, actually we should have done this up here. Whenever you've got changes, delta S and delta G, we always want to put a sign on it. Okay, these values all came out as positive. So it's actually good practice just to say plus, plus, plus. I think it's always a good idea just to make sure you put a sign on it. So if delta G comes out as plus 128 or plus 129, if you round it up, what does that tell us? That shows us that this reaction is not feasible, because from there we can see that delta G is greater than 0. So therefore, the reaction is not feasible. Okay, remember, for a reaction to actually be feasible, we need to have delta G be negative. So the reaction is not feasible, so calcium carbonate is stable. It's not going to do its thermal decomposition. So that's that bit. We've done that, show that it's stable at room temperature. And now finally, we need to calculate the minimum temperature needed to decompose it. Okay, so that's what we've just said, right? At this temperature, the decomposition won't work. Okay, so therefore, what temperature does it need to be at to make it work? What's the minimum temperature to make this work? Okay. Now, the trick to these questions, you get questions about calculating the minimum temperature, or you might get questions calculating the maximum temperature, just depending on which way around the enthalpy and the entropy changes are. For this, we've just said that we need delta G to be less than 0 for the reaction to be feasible. If delta G is more than 0, it's not feasible. So the cutoff point for when it becomes feasible is when delta G is equal to 0. Okay. So that is going to give us the maximum or the minimum temperature, because that's the point at which it's just going to start to work. Well, if delta G is equal to 0, then we can put in our equation here. So we can say delta H minus T delta S is equal to 0. And now we can rearrange this to get the temperature. Okay. So we can change this to be delta H equals T delta S. And then we can get the temperature is delta H divided by delta S. And now we can substitute our values in. Okay. Delta H value was our plus 178. And our delta S value was our plus 0.165. Okay, again, we're using this number, not this number. Okay, because it needs to be in the right units. Delta H was in kilojoules, so this needs to be in kilojoules. So we can calculate that. So we're going to do 178 divided by 0.165. And we get 10, so I'm going to round that up to 1079. And that is going to be in units of Kelvin, isn't it? Okay. Does it say, it just says, if we go back to the question, it just says calculate the minimum temperature. It doesn't say what units they want it in. So we could just leave it like this. Or we could say, if we take away 273 from that, we're going to get it's 806, isn't it? So you could say it's 806 degrees C. Okay. That would be fine to do it in Kelvin. That would also be fine. Okay, because it didn't say in this particular case. But it's worth watching out for that, just to see, do they specify what units they want it in.